In this chapter, we're going to look at cardiac output, blood flow, and blood pressure and how they are regulated. So the first thing we're going to discuss is cardiac output. And the mathematical formula for this is really quite simple. Cardiac output is going to be the amount of blood that's being pumped per minute out of the heart, out of the ventricles. And so cardiac output is going to be measured in mils per minute, and this is going to equal the stroke volume, mils per beat, times the heart rate, beats per minute. Okay? So if you do the math on this, mils per minute, mils per beat times beats per minute, then is going to equal mils per minute. The average heart rate is typically resting heart rate is about 70 beats per minute. The stroke volume is 70 to 80 mils per beat. And so the average cardiac output is somewhere around a little bit more than 5 liters per minute. We have about 5 liters of blood in an average size individual, so you're pumping your entire blood volume about once per minute. So let's take a look at the things that control. And the simplest that control cardiac output, the simplest part of this is controlling heart rate. And if you remember, heart rate is regulated by the spontaneous depolarizations of the SA node, the pacemaker cells that drive the rest of the heart. And this is activated by these HCN channels, the hyperpolarization cyclic nucleotide channels that are sodium channels. They allow sodium to come in and they reach threshold, and then you get the upstroke of the action potential carried by calcium in these particular cells, and then the downstroke followed by potassium. As this hyperpolarizes, that activates the hyperpolarization part of these HCN channels, and then you open those sodium channels again, and you get the next action potential. Sympathetic norepinephrine and epinephrine then activate these HCN channels. They do the CN part, the cyclic nucleotide. Norepinephrine and epinephrine bind onto beta receptors, which activate adenylate cyclase. Adenylate cyclase then converts ATP to cyclic AMP. And cyclic AMP is the cyclic nucleotide then that binds onto these channels and causes them to open more quickly, as shown in this middle diagram here. You can see the heart rate now is up with sympathetic activation. Parasympathetic slows it down because acetylcholine binds onto muscarinic receptors, and those muscarinic receptors activate G proteins that open potassium channels. And so potassium is going out at this point in time here at the same time that sodium is trying to come in, and as a consequence of that potassium leaving, this slows that rate of depolarization down, and it takes longer to reach threshold, and it slows down the heart rate. So both the parasympathetic part and the sympathetic part are regulated then by the cardiac control centers of the medulla that we discussed in more detail in Chapter 8. So thinking about cardiac rate, recognize again we have these two antagonistic effects. That is, sympathetic is going to increase heart rate, parasympathetic is going to decrease heart rate, and these are referred to as chronotropic effects, chrono being time. And so the positive chronotropic effect happens as a consequence of epinephrine and norepinephrine, and this is going to increase the rate. A negative chronotropic effect happens because of parasympathetic acetylcholine causing an opening of the potassium channels, and it's going to decrease of the heart rate. So this shows the effect of sympathetic and parasympathetic in different parts of the heart. We're going to look at the SA node, the AV node, the atrial muscle, and ventricular muscle. So as I mentioned, at the SA node, the rate of depolarization increases with epinephrine and norepinephrine, and the rate of depolarization slows with parasympathetic acetylcholine. The AV node conduction velocity in the AV node is increased a little bit with sympathetic. That helps to conduct that activity from the atria to the ventricles more rapidly, and is decreased with parasympathetic. Parasympathetic has pretty much no effect on the strength of contraction, but sympathetic, as we'll get into it a little bit here, has an increased ability to enhance contractility, the strength of contraction at any given muscle length, and both in atrial muscle and ventricular muscle. So now let's take a look at the things that regulate stroke volume. Remember, the cardiac output is a function of the stroke volume times the beats per minute. So we just looked at the things that control beats per minute, heart rate, but now let's look at what controls stroke volume. And this is a bit more complicated. So there are three variables. There's end diastolic volume, arterial blood pressure, and then on this next slide, contractility. So let's look at these in more detail. End diastolic volume. We've discussed this before. This is the amount of blood that's in the ventricle right at the end of ventricular diastole when it is as full as it can be. This is sometimes referred to as preload because this is the load put on the ventricular muscle prior to it entering systole, prior to it starting to contract. So it's called preload. As you increase end diastolic volume, you're going to increase stroke volume. The more blood you put into the ventricles right before it starts to contract, the more blood you eject. Arterial blood pressure, which is affected by total peripheral resistance. As resistance goes up, arterial blood pressure goes up. This is holding the aortic valve. We're going to talk about the left side of the heart, the aortic valve closed. And so this is sometimes referred to as afterload. This is the force that is put onto the ventricle to open that valve after it starts to contract, after it enters systole. So hence it's called afterload. As you might imagine, the higher the arterial blood pressure and the more it's trying to hold that aortic valve closed, the more it's going to prevent the blood from ejecting during systole. So it's going to reduce the stroke volume as the arterial blood pressure goes up. So as the blood pressure goes up, the afterload goes up, the more the stroke volume is reduced. Now, the other part of this component then is contractility. And so this is how vigorously does the muscle want to contract at any given stretch. And so as you'll see, the more you stretch out the muscle fibers, the more you enhance the strength of contraction. This also leads then to something referred to as ejection fraction. This is the percentage of the blood that is ejected from the heart with one ejection, with one systolic phase. And so it's the percentage of the end diastolic volume that leaves. So it is the stroke volume divided by the end diastolic volume gives you the ejection fraction. And typically it's about 60%. It goes up with exercise. So the other part of this is the effect of stretching the heart muscle and on the ability of the muscle to vigorously contract. And so this is referred to as the Frank-Starling law of the heart. And the way this works is as you increase the end diastolic volume, you increase the stretch of the muscle fibers and you get a more vigorous contraction, increases contractility. So here we're looking at ventricular end diastolic volume. As this goes up, the strength of contraction goes up. What's also in this figure is when we add sympathetic activation onto this, epinephrine, norepinephrine, via beta receptors, this is going to enhance contractility at any given muscle fiber length. And as you can see, you get a pretty substantial increase in the stroke volume, the contractility, as you add on norepinephrine or epinephrine. So intrinsic control of contraction strength. This is the Frank-Starling of the heart. This is simply as you stretch the sarcomeres. So here's a sarcomere that's fairly collapsed, and as we stretch this further and further and further, you get an increase, a dramatic increase in the strength of the contraction. The more you stretch those sarcomeres apart, the more opportunity there is for the actin and myosin fibers to interact with each other, and there's also an enhanced sensitivity to calcium as well. And so these together then combine to make the strength of contraction greater the more and more you stretch the muscle fiber. Frank-Starling law of the heart is what that's called. Okay? So this works to help to adjust for short-term changes in peripheral resistance. So if you increase peripheral resistance, you increase blood pressure. If you increase the blood pressure, you increase the afterload. If you increase the afterload, you decrease the stroke volume. If you decrease the stroke volume, this means there's an increase in end systolic volume because, well, you didn't eject as much blood with that contractile phase. And so there's more blood left over, the end systolic volume goes up. If the end systolic volume goes up, and then you get the same amount of blood coming in during the next diastolic phase, then the end diastolic volume is going to increase because you've got more end systolic volume left over, and you're going to add to that the blood that's coming in during diastole, and so the end diastolic volume goes up. So even though there's an increase in peripheral resistance, there's an increase in afterload, the next heartbeat then may recover that loss of stroke volume that occurred as a consequence of that, because now the muscle is going to contract more vigorously because of that extra stretch with the extra end diastolic volume. So this helps to compensate then for changes in peripheral resistance. Now, there's also extrinsic control of contractility, and again, this is an enhancement that occurs as a consequence of epinephrine or norepinephrine. This is called a positive inotropic effect. So epinephrine and norepinephrine have a positive chronotropic effect, an increase in heart rate, but on top of that, they also cause the muscle fiber to contract more vigorously. Part of this is an enhancement of the ability of calcium then to bind and cause then a more vigorous contraction and interactions between the actin and myosin filaments, and so you get a more vigorous contraction for a given stretch of the muscle. Acetylcholine doesn't have any direct effect on inotropic effect. It does not increase or decrease contractility in any significant way, but it does have a negative chronotropic effect, so the heart rate slows down. As a consequence of that, there is a longer period of time where you're going to be in diastole. Because of that longer period of time in diastole, you get a larger end diastolic volume. Because of that increase in the end diastolic volume and the Frank-Starling law of the heart, this is going to increase the contraction strength. So the stroke volume is going to go up as a consequence of this. So even though the heart rate is going down, which would reduce cardiac output, stroke volume goes up, which would help to compensate for that. Now, it turns out the stroke volume that goes up as a consequence of this is not enough to completely compensate for the slower heart rate. So cardiac output does decrease. It just doesn't decrease as much as you might expect simply for the slower heart rate. So this diagram here shows these graphs of the effect of norepinephrine or epinephrine on contractility and the strength of contraction. So let's look here at about 85%, say, of the optimum stretch of those sarcomeres, and you can see that the relative tension is only about 20% of maximal. But if you add epinephrine or norepinephrine to this, you can see it jumps up dramatically. Here it's about 70%, so it goes from about 20 to 70 for the same stretch of those sarcomeres. This is this extrinsic control of contractility. So cardiac output then is going to equal heart rate times stroke volume. And as we mentioned, the heart rate's the simpler one of this. Parasympathetic slows this down. This is what's meant by that dashed line, is it's having a negative effect on heart rate. Sympathetic activation is going to increase the rate of depolarization of those pacemaker potentials, and so it's going to increase cardiac rate. Stroke volume is more complicated. There's a whole variety of different things that are affecting that, as I mentioned before. One is the increase in peripheral resistance, which is going to increase arterial blood pressure, which is going to hold the aortic valve shut more. And so this is going to increase afterload, which is then going to decrease the stroke volume. On the other end of this, there's a variety of ways in which the stroke volume is enhanced. As end diastolic volume goes up, you stretch the muscle. That's that Frank-Starling law of the heart, the intrinsic control of contractility. And so that's going to cause an increase in the stroke volume. And then also, the parasympathetic activation has its own effect on contractility, enhances contractility at any given muscle fiber length. And so this is going to increase stroke volume as well. All these things that increase stroke volume are going to increase cardiac output. And this component here, the peripheral resistance, mean arterial blood pressure, increases in afterload, are going to decrease stroke volume.